Hello. Hello students. Today we are going to study very important section in ray optics, that is refraction at curved surfaces and lens. In case of lens we will study lens classification, convex lens and concave lens and combination lens and how to calculate power. So let's start refraction from curved surfaces. While solving the problem for reflection at curved surfaces, we will be using this formula. Mu2 upon V minus mu1 upon U equal to mu2 minus mu1 upon R. In this formula, what is U, what is V, what is R, what is mu1 and what is mu2? Dear students, in this formula, U is position of object from reference point, that is pole. Remember, pole will be selected at that surface from where refraction is taking place, okay? And V is position of image from reference point, and R is position of center of curvature from reference point. And dear student, what is mu1? mu1 is refractive index of medium in which object is kept. Refractive index of medium in which object is kept. Object is kept means the medium in which incident rays are coming. Mu2, refractive index of medium in which image is formed. This formula is applicable even for plane surfaces. For plane surfaces, we will keep R equal to infinity. And also, dear student, if the object is present at the refracting surface itself, then refraction from that surface need not to be considered. If the object is present at the refracting surface itself, then refraction from that surface need not to be considered, okay? And what about the sign convention? We will follow the same sign convention as we followed in case of mirror, okay? All distances measured in the direction of incident ray will be taken as positive, while distances measured opposite to direction of incident ray will be taken as negative, okay? And no sign will be given to unknown quantity, and whatever sign will come after solving the problem will be actual sign for unknown quantity, okay? That's what about the sign convention. What about the magnification in this case? The magnification in this case, that is height of image upon height of object, we will be writing mu1v upon mu2u. Value of u and v will be kept as per their actual sign. Okay. And the meaning and interpretation of magnification will remain same. Okay, as we discussed earlier. If the value of magnification is greater than 1 means what? Image is magnified. If the value of magnification is very greater than 1 means image is highly magnified. If magnification equal to 1 means image is of same size as that of object. If magnification is less than 1 means what? This is a diminished image. Okay. If magnification is very less than 1, this is a case of point size image. Okay. Now let's see the problem that will make your fundamental more clear. This is a transparent sphere made up of material having refractive index mu, and radius of the sphere is r. Okay. Now dear student, a light ray is coming from here and converging here. This is coming from infinity. We have to determine the value of mu. Okay. Now we will consider this point as a reference point pole. So u equal to what? Minus infinity. And v is what? This is 2r, because this is r and this is also r. So v is 2r. Okay. And mu1 is what? Mu1 is 1, because this is air. And mu2 is what? Mu2 is mu, because image is getting formed in this medium of refractive index mu. So dear student, let's apply the formula for refraction from curved surfaces. Okay. Mu2 upon v minus mu1 upon u equal to mu2 minus mu1 upon r, and r will be positive because incident rays are coming from this direction. Center of curvature is here. Distances will be measured from this reference point pole. Okay. All distances measured in the direction of incident ray will be taken as positive. Okay. So dear student, mu upon 2r equal to what? Mu upon mu minus 1 upon r. R will get cancel. Okay. So what we are getting? Mu equal to 2, mu minus 2. So mu equal to 2. Okay. This is what is the answer for our question. In this way, we can solve any question. Okay, by applying proper sign convention. Now, dear student, let's see about the lens. First, we will see lens classification, combination of lens, defects in images by lens and removal, and optical instruments. All things which we will discuss only for thin lens. Okay. If it is a case of thick lens, then we will apply formula for refraction from curved surfaces. Okay. So dear students, today we will try to discuss these things. Okay. Lens classification, combination of lens. Let's start. Lens classification. The lens is broadly divided into convex lens, that is converging lens, and concave lens, that is diverging lens. Okay. convex lens or converging lens. Concave lens or diverging lens. A lens is said to be a convex lens when it tries to converge the light rays. A lens is said to be a concave lens when it tries to diverge the light rays. Okay, let's see. Some definitions also we will be looking here. Let's concentrate on this picture. Let us assume the refractive index of lens material is mu and refractive index of surrounding medium is mu, and we are assuming that mu L greater than mu m. This we have assumed. Okay, this we have assumed, and now we are analyzing the things. Let us assume the radius of curvature of first surface is R1 and second surface is R2. Okay, now dear student, this first surface is made up of this sphere, okay, whose center is somewhere here, and the second surface is made up of this sphere whose center is somewhere here, okay. The line joining C1 and C2, that is center of curvature, is called principal axis, okay. This is called principal axis. Now, dear student, if light ray is coming from here, then for numerical calculation, distance is measured in the direction of incident ray, we will be taking positive, okay. So this R1, because the center is located here, so R1 will be taken as positive and R2 will be taken as negative, okay. Now, join this point from here to here. This line is normal, okay, because any point joined with the center of curvature becomes normal. This light ray is moving from rarer medium to denser medium, as it is given mu L is greater than mu m. When light ray move from rarer medium to denser medium, it shifts towards normal, okay. So it will shift towards normal. Now, dear students, we will join this point with this point. Now, light ray is moving from denser medium to rarer medium, then what will happen? It will shift away from normal. So what this lens is doing? This lens is converging the light ray. So this lens will called convex lens. If mu L remains greater than mu m, then lens classification can be made equally with on the basis of shape also. If lens is thick in the center and thin at the surrounding, then lens is a convex lens, okay. But always we do not make classification on the basis of shape, okay. The general way to classify any lens is what? If any lens converges the light ray, we say that lens to be a converging lens, okay. So this lens is converging lens, that is convex lens, okay. In a very similar way, we can classify convex lens also. So dear students, let's start our classification journey. Lens classification. First, we are classifying convex lens. We are discussing only the case where refractive index of lens material is more than refractive index of surrounding medium, okay. Refractive index of lens material is more than refractive index of surrounding medium, okay. This we have assumed everywhere now. when radius of curvature of both the surfaces are different, this type of lens is called biconvex lens. When radius of curvature becomes same, this is called equiconvex lens. When one surface becomes plane, means radius of curvature infinity, and one is curved, this is called plano-convex lens. This can be of this type also. Here r equal to infinity and this is r. And if lens is of this type, this is R1 and this is R2. Dear student, R2 is more than R1. This is called concave convex lens in this condition, okay? So this is the broad classification of the convex lens, okay? Now we will be looking for concave lens. The radius of curvature is first surface is R1, second surface is R2. If R1 is not equal to R2, then this is called biconcave lens. And we assumed here refract index of lens material is more than refract index of surrounding medium, otherwise condition will get changed, okay? So dear student, look at this case when R1 equal to R2. This is called equiconcave. And this is a case of plano-concave. This R equal to infinity and this is R. This is called plano-concave lens. This is thinner at the center and thicker. And this is a concave lens, okay? Thinner at the center and thicker at the surrounding, okay? This is the broad classification of the convex and concave lens. Now, let's see lens maker formula to solve lens problem, okay? Lens maker formula. To solve thin lens problem. This formula is applicable in a condition when lens is a thin lens, okay? And medium on both the side of lens should be same, okay? Then only this formula is applicable. The formula is like this. Power of the lens equal to 1 by f equal to mu lens minus 1 upon R1 minus 1 upon R2. R1 and R2 are the radius of curvature of the two surfaces of the lens, okay? Power will be written 1 by f. When f is in meter, then unit of power will be in diopter, okay? If f is in centimeter, then we will be writing 100 upon f. R1 and R2 we will keep with sign, okay? And this is the lens formula. 1 upon V minus 1 upon U equal to 1 upon F, where magnification equal to size of image upon size of object equal to V upon U equal to F upon F plus U. Dear student, let's start with the problem solving so that we can understand the concept in more deeper way. Suppose this is a case of thin lens having refract index 1.5 and radius of curvature of the two surfaces R1 equal to 20 centimeter and R2 equal to 30 centimeter, and the lens is kept in air. The condition for thin lens formula to be applicable, lens should be thin and medium on both the side of lens should be same. So condition is matching, okay, so lens formula is applicable. Now we can easily determine the focal length. Let's start. 1 upon F, focal length in air equal to mu minus 1. 1 upon R1, R1 is positive and R2 is negative here in this case. So after solving this, we will get 0.5. Take 60 as LCM, this is 3 plus 2. So this is 5 upon 60 means 1 upon 12 means 1 upon 24. So dear student, the focal length in this case of the lens is 24 centimeter. If you are interested in looking at the power, then this will be 100 upon 24 diopter, okay. This is the first case. Now we are modifying this question again. If this lens is kept in water, water means refract index 4 upon 3, then what will happen to the focal length and power of the lens, okay? What about whether nature of the lens will get changed or not, okay? This also we will see here. Dear student, now lens is kept in water. Now let's start problem solving. We can write 1 upon F in water equal to what? Mu minus 1, mu relative, mu lens with respect to medium, that is water, minus 1, 1 upon R1. R1 is positive and R2 is negative again. This 3 upon 2 upon 4 upon 3 will become 9 upon 8. 9 upon 8 minus 1 means 1 upon 8. And dear student, this is 1 upon 20 plus 1 upon 30. We will take LCM 60. 60 means 3 plus 2. 5 upon 60 means 1 upon 12. So dear student, in this case, focal length is coming 96 centimeter. So when lens is kept in water, its focal length becomes 4 times, means power becomes 1 by 4, okay? So what will be corresponding diagram? See, if the diagram in air is like this, then dear student, diagram in water will be like this. The diagram in the water like this. Okay, this will become 96. This has become 24. Means power has decreased, okay? Focal length has increased. But nature of lens is not changed, okay? lens was earlier also convex, now also it is convex. Okay, now look at another question. Dear student, now you can also try. Refract index of the lens material is 1.5, R1 is 20 age earlier and R2 is 30 age earlier. Now we are keeping this lens inside a material whose refract index is more than lens material. Let us assume refract index of surrounding is 2. Then what happens to the focal length and power, okay, and nature of the lens? You will find that when lens is kept in a medium of refract index more than the lens material, focal length will increase. Focal length always increases, okay, power decreases. But in this case, nature of lens will also change. Earlier lens was behaving as a convex lens. Now you will find lens will start behaving as a concave lens, okay. Let's see. Always remember, focal length of convex lens is positive and focal length of concave lens is negative. Let's see the solution. Now what is 1 upon f in this medium? 1.5 upon 2 minus 1. 1 upon R1 minus 1 upon R2 we are writing directly, okay. This is minus 0.5 upon 2. This is 1 upon 12. So dear student, this F medium is coming as minus 48. Earlier it was plus, but now it is minus, okay. So what you observed? Focal length is increased, power is decreased, but nature of lens has changed. Now lens has started behaving as a concave lens. Look at the diagram of this lens. In this case, picture of the lens will be like this. It will behave now like this. This focus is secondary focus, okay, where light rays coming parallel to principal axis converges, okay. So dear student, now we will see fourth option of the similar type, okay, that is the last option, okay. Now see, in the same question, suppose lens refract index is 1.5, the radius of curvature of the first surface is 20 and radius of curvature of the second surface is 30 centimeter. Now dear student, what we have done? We have kept the lens inside a material whose refract index is same as that of lens material, okay. This case is also very popular and usually asked in the competitive examination. Now dear student, mu medium equal to 1.5, okay. Now in your mind, hope answer could have come. Now let's see what happens. 1 upon f medium equal to what? Mu 1.5 upon 1.5 minus 1. 1 upon R1 minus 1 upon R2 I am writing directly, okay. This becomes 1 upon f equal to 0. Means dear student, f medium is infinity and power is 0 in this case, okay. Many students commit mistake while writing the nature of the lens. Sometimes many students write this will behave as a plane mirror. This is not the case of reflection, bachcho. This is a case of reflection. This will not behave as a plane mirror. This will behave as a plain glass slab. This will start behaving as a plain glass slab, okay. So the diagram of the lens will be like this, okay. This will start behaving like this, okay. This lens will behave like this, where power is 0 and focal length is infinity, okay. This will behave as a plain glass slab. Plain glass slab. Now I am generalizing the results, okay. Whenever any lens is kept in a medium other than air, then remember of refract index more than 1, okay, then what will happen? Focal length will always increase, power will always decrease, okay. but nature of lens will not change until and unless refract index of surrounding is not more than or equal to refract index of lens material. If it is equal, then what will happen? It will not be even a lens, it will be a plain glass slab, okay? But remember, if the lens is kept in a medium of refract index which is more than refract index of the lens material, then nature focal length will increase, power will decrease, but nature of lens will also change. If earlier lens was convex, it will behave as a concave. If the earlier lens was concave, it will start behaving as a convex, okay? So dear student, this was all about the lens classification. Now we will see lens combination, okay? Lens combination. Let us assume these are two lenses, thin lenses, okay? If it is having focal length f1, focal length f2 and separation between optical centers d, then equivalent focal length is given as 1 upon f1 plus 1 upon f2 minus d upon f1 f2. And what is, dear student, P equivalent? The P equivalent equal to P1 plus P2 minus D into P1 P2, okay? Remember, in the numerical problem, focal length for convex lens, we will take positive, and focal length for concave lens, we will take negative. When separation between optical center is 0, then directly 1 upon f equivalent will be becoming 1 upon f1 plus 1 upon f2, okay? Like that we can add, okay? Now dear student, let's see what happens in case of cutting of lens. What happens in case of cutting of lens, okay? See, let us assume this is a thin lens, equiconvex lens, okay? Having radius of curvature, this is R, and this is mu. So dear student, here P equal to 1 upon F equal to mu minus 1, 1 upon R1 minus 1 upon R2, okay? So here we are getting mu minus 1 into 2 upon R. So F is what? R upon 2 mu minus 1. This is F, okay? This is F, okay? And remember, intensity is directly proportional to exposed area. Now dear student, what happens if this lens is cut in two equal parts like this? Then what will be focal length and power of this shaded portion, okay? See here, if we see here, 1 upon f dash equal to p dash equal to what? Mu minus 1, 1 upon r1 minus 1 upon r2, okay? So dear student, what is f dash? R upon mu minus 1, this will be 2f. So focal length has become twice and power has become half, okay? So focal length has become twice and power has become half, but intensity will not change because exposed area is same, okay? So intensity here is same, okay? Now let's see another case also. What happens if the lens is cut like this along principal axis, okay? So dear student, now neither R1 change nor R2 change, so focal length will not change, okay? Now, what about neither focal length is changing nor power is changing, but what about intensity? Because exposed area has become up, intensity will become I by 2. Okay, so intensity has reduced to 50%. Okay, so hope you understood the lens classification and combination of lens. You can solve any such type of problem in the exam. In the next lecture, we'll be seeing defects in images formed by the lens, okay, and displacement method. Thank you.